Thank you very much, Daniel. I'm very happy to be with you here today. Came all the way from Brazil, but as Daniel said, we are always involved with the Python communities in the US. My company, Vinta, works mostly with clients from the US, and we are always contributing to open source and other projects. So in case you want to know more about us, I'll give the link for the slides, and you can click on this logo here. And we are a software consultancy that builds web products, mostly from clients here in the US. So in case you need help with development help with Python, Django, React 2, feel free to reach us. And I'm here to talk about 1 + 1 = 1, or record deduplication with Python. And that's a problem we faced with a client at Vinta, and I'm going to show you the ways, the methods we use to solve it. Hopefully you enjoy. Slides are available here. These slides are Jupyter notebooks. Not sure if you'll be able to install everything that's needed, but you can follow them by checking this link. It's a GitHub repository. Okay, so first an introduction. Why is it a problem? Why the duplication is a problem? Mainly because real-world data is inputted by people, and it's often not reviewed, not linked with related data, not properly normalized by the input system. You can have like a date field that accepts wrong days for February or leap years or things like that. Or simply it's incorrectly inputted by people because people make mistakes like typos, mishearing, miscalculation, misinterpretation, etc. So real-world data is generally bad. And this causes the following problems. The lack of unique identifiers, making it difficult to detect duplicates in a data set or to link one data set with another. Duplications, multiple records referring to the same person. That happens a lot in any kind of product or platform. Inconsistencies, like a person with multiple addresses. Maybe the person changed the address but didn't update all records, something like that. Bad formatting, like various formatting for date times, things like that. And all of that affects the ability to extract knowledge from one or more data sets. And the solution to properly extract knowledge from fuzzy data sets is to perform record linkage. And it works by joining records in a fuzzy way. You use names, addresses, phone numbers, dates, things like that, to join records. And this term, record linkage, is mostly used when the linkage is applied to multiple data sets. Like if you want to join a restaurant food inspection data set with an employee wage data set, to figure out if like lower paid employees, better paid employees will have a consequence on the food quality, maybe. And someone did that, and there is a correlation. Yeah, as expected. And record linkage is also known as data matching, entity resolution, and other names. What we're talking about here is a specific application of record linkage that's called deduplication, which is applying record linkage to a single data set, applying record linkage against the data set itself to figure out which records are duplicates. Here's a very simple example. I'm creating a pandas data frame here and we have here a restaurant, name, address, and city. As you can see, the data, we don't have a perfect equivalence between the rows. And a good deduplication over this data, we found out that 0 and 1 are duplicates, 2 and 3 are duplicates, but 0 and 1 and 2 and 3 are different, despite being similar, despite the address being similar, the city being the same, the name being similar. Those are different clusters of data. So as you can see, it's not trivial to do that. You have to use different techniques to figure this out. Okay, so how's that process of the duplication? Usually you get a data set, you pre-process it, and then you get a cleaned data set. Then you index on it, you perform indexing to extract which pairs you want to run comparisons on. And then you run the comparisons, you get the comparison vectors. With the comparison vectors, you can classify them as matching or non-matching pairs. And finally, you want to cluster unique record clusters. I'll explain that better later. Let's follow each of those steps. So without unique identifiers, we need to match records by fusing data like names, addresses, phone numbers, dates. Those are kind of the most common types of data we have to handle, so we'll learn how to clean them. First, names. Usually we're talking about companies or people names. We will use string functions and regexes to normalize names and remove undesired variations. Like I have here a very simple list of names, company names, Apple, the various names Apple had in history, Apple Computer, Apple Inc., Apple Company, Computer Company, etc. And to clean this list, to figure out that all of them are Apple, sorry, I think I jumped a lot here, sorry. Oops. Okay, here again. Okay, so to clean this data set, I'll just put it all lowercase because the case doesn't matter here. I'll remove irrelevant separators like commas, dots with a simple regex. Then I'll remove multi-spaces that were produced by those substitutions, and I'll get only single spaces. And then finally, I'll remove stop words, words that I don't care about. Like if I'm working with companies, they can be one day incorporated or changed to corporation or things like that. So I won't care if it's company, corp, corporation, incorporated, LLC. So those are my stop words here. I could get this from somewhere, or I could calculate that from my data set. And by removing those business stop words, I get that the entire list is made of Apple names. That's very simple, but it's not very precise, obviously. We can use more smarter ways to process this. We could use a natural language processing library called probable people that can parse company names and extract just the parts we want. Here, using probable people, I pass Apple Computer Corporated, and I get that Apple is a corporation name, computer is part of the corporation name, and incorporated is a corporation legal type. If I don't care about the legal type, I can use this library to parse the names and extract just the parts that I want. Doing it again now with the probable people library, I get this, which is also good. And probable people, as the name suggests, can parse people names too. If I pass Mr. Guido van Halson, figure out that Mr. is a prefix, Guido is a given name, Van Rossum surnames. But performance isn't great for non-English names. So you can try name parser, which is not probabilistic. It uses like huge lists of names. So if I pass my name, Flávio Juvenal da Silva Jr., to probable people, it thinks that I'm a company. I'm not there yet. But if I use name parser, it figures out correctly that Flávio is my first name, Juvenal is my middle name, da Silva is my last name, and so forth. And that's also a thing that's worth talking about. People in Brazil have like 3 or 4 last names. So when people ask, what's your last name? I'm like, oh, I have like 3 last names, but okay. If it's useful to ignore accents, you can try Unidecode. Unidecode performs ASCII transliteration, which is like trying to find the ASCII character that matches best what you are passing. So if I'm passing my name with the accented A, I can get Flávio without the accented A. It's important to consider how the data values were inputted. If the value was inputted by someone while hearing from someone else, you can try phonetic encoding with this library called double metaphone. So you can normalize words that sound similar. So Andrew and André is like the Brazilian word for Andrew, they both have a common encoding, common phonetic encoding. So you can figure out that if I'm saying I'm André to someone in the US, maybe they write down Andrew, and I can use this tool here to normalize this kind of thing. Okay, now cleaning addresses. Geocoding street addresses, that is, converting them to latitude and longitude, is a very useful way for matching, because geocoder usually clean irrelevant address variations, and also having the latitude and longitude enables the calculation of geometric distances between addresses. So suppose I have this list of addresses. Those are all Apple historic headquarters, and I geocoded them using this library geocoder. It's using the Google geocoder. And if I do that, I get this. I pass this address here, and this other one that's slightly different, like suite is STE here, Cupertino is Lupertino here, someone mistyped it. And the Google geocoder was able to find the same latitude and longitude for these two addresses. So Google geocoder was able to ignore the lower and uppercase difference, ignore the difference between suite 300 and suite 330. Beauty entries may be the same, or maybe just ignore this. Consider Lupertino as Cupertino, expand abbreviations, all this kind of stuff. That's great for matching. However, when I pass one infinite loop and one written down infinite loop, it gets slightly different addresses, so it's not perfect. And geocoding from web APIs is slow and has quota limits. Alternatively, you can build your own geocoder. There are tools for that. If geocoding is viable, you can't do it, you don't have the resources, you can try a library called PyPostal to normalize addresses. So if you pass one infinite loop like this and one infinite loop like this, and you call expand address, it will expand to this, the same string representation. It will also remove the commas, lowercase, uppercase, all this kind of stuff. So it's good to normalize addresses, but it won't correct wrong addresses. So Cupertino won't become, Lupertino won't become Cupertino. And there are multiple expansions of the address. So STE can mean suite or can mean saint if it's like a French address or something like that. So it gives you different expansions for the address. So it's not a single expansion. Phone numbers are things that are useful to clean too, and you have a library called phone numbers, very descriptive, and it can normalize phone numbers from many countries. You can pass that a US phone number and get the international format for it. It's great because you can ignore variations on formats. Dates, it's very useful to clean. There's this classic problem of date, month, date. Hope someday someone will fix that. And date parser is great because if you pass at 10/1, 10 a.m., and if you pass as, which is the Portuguese for at, 10/1, it will figure out that this one is a US date, so month first, and this other one is a Brazilian date, so day first. And so it figures out the locale of the string based on what's around it, okay? So it's great if you are parsing dates from some source, scrapping dates or something like that. To prove that it's doing this, you can check that locale here is PT, which is Portuguese. Okay, let's clean a real data set. We'll grab a data set called restaurant data set. In fact, I've changed a bit this data set. You can check the diff if you want. But it contains 881 restaurant records, and 150 of them are duplicates. So it looks like this. You have those 3 records here. Clearly, they are duplicates. As you can see, the name is very similar. You have those other ones here. They are duplicates, but it's not very simple. As you can see, the city here changes from Studio City to Los Angeles. But the address is the same. The name is similar. And you have this other case here that is quite difficult because you have Hotel Bel Air Hotel, and Bel Air. And here, RD is expanded to road. So you have all sorts of variations here. And this data set comes with the truth, okay? The truth is here, which cluster each record belongs. Obviously, we will remove this cluster, and we remove the phone column to make things more difficult, and you are left with this: the name, the address, the city, and the type of the restaurant. So with just that, we need to figure out which restaurants are duplicates. Okay, let's clean everything with the techniques we've seen before. We clean the name, removing irrelevant characters, mood spaces. We are here getting the most common words of the name: S, café, de. So I will ignore some of these words because they are very common and doesn't tell a lot about the restaurant. So I remove S, D, la, le, off, and on, L. I remove those words, and I'm left with this. I will geocode all the addresses. So I did that before, and the result is here: address to latitude and longitude. And I also used Google's geocoder to get the postal code of the address. So I'm assigning here, and now I'm left with the name, the address, the city, the type of the restaurant, and things that I got from the geocoder: the postal code, the latitude and longitude. And you can see that it's already working, because here, despite the city being different, the latitude and longitude is the same. That's great. I'll add the address variations from PyPostal. So to normalize things like BLVD to Boulevard. Note that there are different address variations, so there is a list inside each of those values. And now with a clean data set, we can move to the next step, which is indexing. To explain the following, the duplication steps, we use the Python library called Record Linkage, also known as Python Record Linkage Toolkit. We choose it because it doesn't abstract too much the details of the process, but it has a very simple API. We have the cleaned records. Now we want the pairs we want to compare. To produce the pairs, because we want to compare records against records, we could do a full index. We could match all records against all records. But a full index on 881 records produces this large number, more than 300,000 pairs. And the formula for that is this one, the combination, and it appears like this. I get the record 1, A1. I won't compare A1 with A1 because the same. I will compare with everything else. A2, I won't compare with A1 because I already compared. I won't compare with A2 because the same, but I'll compare with everything else. So the formula is that, and the number of pairs grows too fast as the number of record grows. It grows quadratically. That's why we need indexing to produce only the pairs that are good candidates of being duplicates. Otherwise, we waste too much time. Indexing is also called blocking because the trivial way to index is to produce pairs that have some column value in common. By doing this, we produce blocks of pairs like this. A1 to A4, for example, have the same postal code. So I will only compare records on this block here. Here I have another block of common postal codes, but it can happen that some record has a unique postal code and I won't be able to compare it against anything else. So below here, we produce with record linkage, we produce the pairs that have equal values for postal code. So I create a block index postal and call index on the data frame. And I have here 6,000 pairs to run comparisons later and match them. We could also produce pairs by sorting the unique values on some column and getting the records with neighboring values. The idea is to produce pairs that are close on some value of some column, like Johnny and John, or like some date and some date closer to it. It looks like this. So it's more flexible than standard blocking, and it can get slight variations on values. If I do that on the name, okay, so I'll get a sorted neighborhood index for name with Windows 7. So I'll get 3 values ahead and 3 values before for the name. And I produce the pairs, I get 3,000 pairs. And note that this isn't perfect because you won't be able to get variations like Camila with K and Camila with C, because the ordering, the sorting is very sensitive to the leading characters of the strings. There are other ways to handle that. You can check Christian's book. I'll pass the reference later. Okay, but to produce all of these pairs that I want to run comparisons on, I can use various index techniques, but at the end I should union them to avoid like producing repeated pairs. So I union the postal index pairs with the name index pairs, and now I'm left with 9,000 pairs to run comparisons on. Okay, now let's run the comparisons. We want to run the comparisons on the indexed pairs to produce a comparison vector for each pair. A comparison vector represents the similarity between two records by holding similarity values from 0 to 1 for each column. So I have something like this. For the record 100 and 300, the pair 100 and 300, I have equal names, so the similarity value for name is 1. I have similar addresses, 075, and everything else. You get the idea, okay? So to compute those comparison vectors, I have to define similarity functions, the similarity functions I want to use. And I can use record linkage for that. I create a compare object here, and I choose that I want to compare name against name with Jarrow-Winkler similarity. I want to compare address with address with Jarrow-Winkler. I want to compare latitude, longitude with latitude, longitude using some exponential decay on the scale 0.5 and everything else. And I can also build custom comparisons like this one to compare address variations. And to check if the address variation is, has something in common, I'll use an intersection between the variations. And I'll convert it to a float. So if the intersection exists, it's 1. If the intersection doesn't exist, it's 0. There are many similarity functions we could use. We use Jarrow-Winkler, but we could use others. Jarrow-Winkler gives priority to the beginning of the string. Levenstein cares more about the order. LCS cares less about the order. There are many others we could use. Those are only some that are implemented on record linkage. So you can check here the difference between them. If I use Jarrow-Winkler between Annie Morton and Annie Morton of Chicago, I get this value. If I use Levenstein, I get a lesser value because Jarrow-Winkler gives priority to the leading characters of the string. If I use LCS, I get so-so. If I use Jarrow-Winkler on this, the palm and palm D, I get this. Levenstein, I get 0 because the order is completely different, so I get 0. And if I use LCS, it gives a higher value because it cares less about the order. So you have to figure out what do you want to do. If you don't want to care about the order, you can use LCS. There are many other similarity functions. You can check again Christian's book, and you can check the similarity functions implemented by record linkage. Okay, now we'll compute the vectors. We'll just call compute on our similarity functions. And here are the 5 of the vectors. 0 with 1 have these values, pretty high values, except for on type. 0 and 2 have these values here, again, pretty high values. 0 and 3 have these other ones. So we can see here that perhaps 0 and 1 and 0 and 2 are matches. Okay, now with our comparison vectors, we explore different ways to classify them as matches and non-matches. Now classification. Okay, so let's remember what's on records 0 to 5. 0 to 5 I have here, Annie Morton 3 times. 3 to 5 I have Art Daly 3 times. Okay, so these are the things we want to find as duplicates. These and these. I can try a threshold-based classification. It's a very simple way, very straightforward. I just compute a weighted average over the vectors to get a score. So I'll use NP average, get the vectors, and I'll put the weights like 30 for the name, 10 for address, 5 for city, 10 for type, 30 for latitude and longitude, and 15 for address variations. And I get those scores here. As you can see, high scores are matches, and lower scores are no matches. So it's good. It seems to be working. So we will just consider anything that's above 8.5 as a match. That's our threshold. And if we do that, we get this. Those are the matches. 0 and 1, 0 and 2, 1 and 2, 3 and 4, 3 and 5, and so on. Let's check a match we found. What are the matches of record 3? Those are the matches of record 3, 4 and 5. So it seems to be working. Since we have the cluster column, we have the ground truth about our data, we can check how well this classification did. So I'll get the golden pairs. Those are the real pairs on the data. And I'll do some set, subtraction, and difference to figure out how well we did with the pairs we found. So I'll get the found pair set versus the golden pair sets, and I can check that I get these numbers here. A good number of true positives, a lot of false negatives, and some false positives. We got a small number of false positives. Those are really tricky cases, like this one, Ritz-Carlton Cafe Bookhead, Ritz-Carlton Dining Room Bookhead. It's basically the same, but it's not, because of one is the cafe, other is the dining room. So it's quite difficult to figure out this case. But there are other cases here we could have done better, like this one. The others is the same, but the name is completely different and the type is different too. On the other hand, we got a lot of false negatives. We missed a lot of matches. So we missed this match here that should be simple. We missed this other match here that should be simple too. The latitude and longitude is the same. City is very similar. Address, very similar. Name is very similar. Don't know why we missed this, but we missed. We could try different thresholds and everything, but we set all of these by guessing. We set the weights and the threshold by guessing. Could it do any better? Yes, we could try supervised classification. Instead of trying to guess the weights and the thresholds, we can train a classifier, a machine learning classifier, to classify matches and non-matches based on the vectors we have. So we'll produce some training data. So I just produces some training data like this, real matches that I'm giving to the classifier to train it. Okay, so those three here are on the same cluster, so they are a match. Those other here have different clusters, so they don't match this other stuff here. So I'll give this to a classifier. Of course, I have to pre-process the training data, so it's exactly the same as the data we will use to classify. And we'll feed a support vector machine classifier with our training data. SVMs, support vector machines, are resilient to noise. They can handle correlated features like address and latitude longitude, and are robust to imbalanced training sets. That's good, very relevant for deduplication, because usually we find more negative pairs than positive pairs to add to a training set. So SVM seems to be a good classifier for that. You can check Bilenko's PhD paper that details a lot about the best classifier to use on deduplication. Okay, so I'll get the training pairs, get the training vectors. So I'll compute the vectors for the training pairs. I'll create a SVM classifier. There is one on record linkage. And I'll learn from the training vectors and the matches I have on those vectors. And then I'll use SVM to predict from the comparison vectors what means a match and what means a non-match. So I get the SVM pairs. And it performed better than our hand-on method of setting weights and thresholds. It got more true positives and also less false positives. Much better result. The only false positive we got with SVM and not on the threshold is a really difficult case. That's this one. Everything is very similar except for the address. The type is the same, the city is the same, except for the address, everything is very similar. So it's okay that SVM made this mistake. But SVM was tricked by some apparently simple cases. So we can't be very confident. It really learned well to classify matches. It was tricked by those cases here. Again, seems to be a simple case, but it gave a false negative for this. It didn't find this match. It also didn't find this match here. This here is not so simple because since we're using Winkler, we are caring about the order. Maybe if we used LCS, we could have a better result here. There are other classifiers you could use, but the truth is, it's very difficult to build a good training set that takes into account all important cases of matches and non-matches. Also, it's possible to tune the parameters of the classifier to get better results, but it's very difficult to decide the right parameters that will generalize well for future predictions. And there's a very important thing here. We are not even sure the indexing rules we've used are really sane. We've indexed by name, sorted neighborhood of name, and by postal code. But we are not sure this is correct. We could be dropping true positives because we are not blocking them together, so we're not creating them as pairs to compare. And we could be introducing false negatives because we are blocking things together that we shouldn't, and the classifier isn't being able to classify them as non-matching. The alternative to all that uncertainty is active learning classification. Again, it's based on machine learning, but it does a smarter way of classifying things. Active learning methods try to identify training examples that lead to maximal accuracy improvements, both to train the optimal classifier weights, as well as to find optimal indexing and blocking rules. So right now, we are not only trying to find the best weights for the classifier, we are also trying to find the best indexing and blocking rules. There's a library called dedupe that implements that on Python. Let's see this in practice. We have to define the fields of our data. So name is a short string, address is a short string, city is a short string. I have to tell which fields have missing values. Then dedupe also comes with many built-in variables, like for common data types like names, addresses, latitude, longitude, date times, thereby reducing a lot of preprocessing work. It also supports custom variables. So I can say that postal is a short string again, but latitude and longitude is a lot long type. So I don't need to use some smart preprocessing or some smart comparison. Dedupe already handles that for me by just setting the type of the variable for latitude and longitude. And I can set a custom comparator, like Record Linkage. But here I will subtract from 1, because on dedupe, things with higher numbers are farther. It's the opposite of Record Linkage, where 1 is better. Here, higher than 0 is worse. So I just subtract by 1 to get 0 and 1. Okay, another nice feature of dedupe is the ability to model interactions between fields. What's that for? Imagine if we have an exact address match, exact match for city and address. It makes no sense to have address, city, postal, latitude, longitude, and address variation, all of them contributing additively to the matching odds. It's expected all of them to match if address and city match exactly. So to prevent a redundant increase of odds, we should add an interaction between those fields. Interaction is the statistic concept, but it's basically that. You just say that there is an interaction between address, city, postal, latitude, longitude, and address variations because they are all different ways of saying address. That's nice, so I'll initialize dedupe. I'm using here a P-code dedupe that I've trained it before, but I've showed to you how I trained it. Dedupe, you initialize the dedupe with the variables, and dedupe starts asking you for examples of pairs for you to label. So for example, this pair here is a match or a non-match? What do you guys think? Non-match. Okay, so I put N. And then it asks for this other case here, non-match again. Then it asks for this case. It's a match. Okay. And it starts getting more complicated cases. So like this one, where the city is different, the latitude and longitude is the same, the name is slightly different, and yes. And as I train, dedupe starts to learn better the classifier weights and the indexing rules it wants to use. So here it thinks that it's good to use an index rule called fingerprint on address, which is basically sorting the address, and the whole field predicate on name, which means getting if the whole name matches. Obviously, this is not a very good blocking rule because we will miss lots of matches, but as you train, it will learn better blocking rules. Like, it will try something like the sorted acronym for the name. And you try different blocking rules, and after some iterations, I got this. Those are the predicates the dupe learned for me. It learned that the first token of the name should be the same, and the address should be similar, using some TF, DF, and gram metric. Or there should be two common tokens on the name, and the sorted name, the fingerprint of the name, should be the same. So this makes sense. The dupe learned something useful from our training or labeled examples. So that's great, seems to be working. And the dupe selects those predicates from an extensive list of predicates, like all of this. It tries different things, like even integers on values, metaphones of strings, fingerprint, acronyms, suffixes. So it tries a lot of stuff to figure out the best blocking rules. Okay, to proceed with the actual deduplication, we run the dupe threshold to get some threshold, and we run the duper match to run the match, and we get the results. The results were much better than SVM. We got 141 true positives, but we got 2 more false positives too. It found more true positives, but it also found more false positives. It's possible to control that. That's also great from the dupe, is that you can control the recall weight. You can change the recall weight to 0.5, and you can get now less true positives, but also less false positives. So as you can see, there is always a trade-off between true positives and false positives, or more precisely between precision and recall. You have to decide what's more important for your business. And it's great that the dupe provides you with a parameter for that. Okay, but let's suppose we just want more true positives. What about the false positives the dupe found? Those are the false positives. This false positive here on Cafe Lure and Cafe Regio. This other false positive here. This, like, even I would consider that as a match, but actually this isn't a match. But we shouldn't blame the dupe for that. And again, the Ritz-Carlton case, that's very difficult. This Cafe Regio and Cafe Lure thing, maybe cafe could be a stop word, or maybe we could incorporate some logic for name rarity. If the token isn't rare like cafe, it should contribute less with the name similarity than some token like Regio. It's possible to do that with an interaction with name frequency. You can check this issue here for this. Or maybe the duper could learn more restrictive blocking or less weight on name. It's difficult to guess. The false negatives we lost are these ones. Also difficult cases, and we will analyze them better. Some of them could be prevented with better address normalization. Maybe we could train more the deduper. It's difficult to know, but we can try this and evaluate with a test set and this kind of things. Finally, clustering. Using the threshold or the SVM, we got the matching pairs. But what the dupe really returned to us were the clusters of matches. The dupe returned this to us. Returned that 0, 1, and 2 are a cluster, 3, 4, and 5 are a cluster, and everything. So the dupe went one step further in the process and merged the matching pairs into clusters. Why is that important? Because the following can happen. You can have records A, B, and C, and by deduplicating find that A and B are matching, B and C are a match, but A and C is a no-match. And that makes no sense, because how that can be? These two match and A and C doesn't match? Doesn't make sense. So you have to compute the transitive closure of the pairs with clustering. Using some private methods, I have to go fast here, you can get the unclustered pairs from the dedupe. And by doing that, you check that you know that the unclustered pairs are different from the clustered pairs. Okay? And if you look graphically, you see that what happened. The truth is this one, okay? Everything matches here. When you get the unclustered pairs, you get this. Doesn't make sense. You have to connect this, or you have to separate in some other way. And if you cluster, you figure out this. So clustering can introduce new pairs. And that's good because new pairs might be the correct thing. Or something like this can happen. The truth is that everything matches here. Auto Bell-Lair, and Bell-Lair-Hotel. If you get the unclustered pairs, it looks like this. Makes no sense again to this match this and this match this, but this should match this. If you run the clustering, you get this, which is wrong. So clustering can both improve or either improve or decrease your correct pairs. And you can control that with the recall weight parameter we saw before. And that's it. I don't have enough time. Make sure to check dedupe product version. If you don't want to write code to dedupe stuff, you can check the product version of dedupe. And there are next steps, but you can check them on the slides. Thank you very much.
Thank you very much, Flávio. We have time for just 2 questions. Anyone?
Any question?
I have one question, actually.
Okay.
But I will obviously give priority to the audience. All right.
Does dedupe or any of the tools that you were using sort of maybe introduce an epsilon between latitude and longitude so that, you know, latitude and longitudes that are very close together but not exactly the same count as a match or not?
You mean if they include, sorry, what exactly?
So if 2 latitudes and longitudes are very close to one another but not exactly the same, does dedupe count that as a match or not?
Yeah, depends on the weight. Depends on the weight, it will put on the similarity value for it. But on record linkage, you can control that more with that decay parameter. If you use an exponential decay, it will decay faster than if you use something else.
Anyone else?
Any other questions? Make sure to check incremental record linkage. What happens if new records come? You have to figure out if you want to break clusters, create new clusters, this kind of stuff. And data fusion, because you get the pairs, what about them? Some may have older addresses, some have new. Check data fusion to figure out the best way to merge all the matching pairs into just one record. Thank you very much.
Thank you.